the discussion was always sort of trapped in a physics lab.
Right, it was all theory, maybe some experimental results in a paper.
Exactly, or a prototype locked away somewhere. But today, that story has fundamentally shifted. We're now watching this transition from pure physics to commercial, real-world hardware, stuff people can actually buy.
That is the perfect way to put it. The whole focus has moved. It's not about the question, can we do this anymore? It's now an industrial engineering problem.
Right.
It's about who can build a manufacturable, scalable machine and actually sell it to a paying customer. That bridge is, I mean, it's the hardest part of this whole sector.
And that transition is precisely our mission today. We're doing a deep dive into Rigetti Computing, one of the earliest public players in this space.
A really interesting one, too.
We're going to unpack their full stack strategy, look at the extreme tech that makes their systems work, and really understand the aggressive roadmap they've laid out. Okay, let's unpack this. How is a company that started in a startup incubator selling physical quantum computers to industrial clients today?
It all starts with their fundamental approach, this full stack model.
Okay.
From day one, they made a strategic call to control the entire technology chain, top to bottom.
You have to think, in this industry, that's not just a business choice. It's almost a necessity, right? You can't just order a quantum chip off the shelves.
Exactly. The supply chain for this stuff, it's basically non-existent. So by controlling the stack, Rigetti designs and builds their own QPUs, the quantum chips, in-house.
And not just the chips.
No, they also build the complex classical architecture that runs the chip, and, this is crucial, they develop the software platform on top.
So that vertical control minimizes their dependencies.
I'd argue it's their core business advantage right now.
Yes, and that control starts physically in California, right?
Uh-huh.
Tell us about the infrastructure behind this.
That would be Fab 1 in Fremont. It's their in-house manufacturing facility, and it's dedicated exclusively to quantum device manufacturing and rapid prototyping.
Which gives them a huge speed advantage.
A huge advantage. While competitors are relying on, academic labs or government facilities, Rigetti is literally rolling its own chips. The iteration cycle is just so much faster.
So that's the hardware. How does a user actually talk to it? On the software side, there's Forest.
Forest is the entry point. And at its core is a custom instruction language they developed called Quill.
Quill, as in Q-U-I-L.
That's right. Quantum instruction language. Think of Quill as the essential translator. It lets programmers write algorithms using standard Python tools, which they already know, and it makes sure that code can talk seamlessly to the quantum chip.
Which is key, because these devices aren't standalone machines. They're accelerators. They have to work with classical computers.
Absolutely. They have to play nicely together. And, stepping back to their origins, this path wasn't a sure thing. Chad Rigetti, a physicist from IBM, started the company back in 2013.
Their early days are classic Silicon Valley lore.
Oh, totally. They were in Y Combinator's 2014 batch, and they were immediately labeled a space shot company.
High risk, sky high potential.
Exactly. They got some major early venture funding, Series A and B, from players like Andreessen Horowitz. Then came the big move, going public in March 2022.
Through a SPAC merge.
A SPAC merger, yeah. They're now trading on the NASDAQ Q under RGTI.
And going public that way, as you know, it throws you into the deep end.
Yeah.
It demands aggressive growth and results in a very short timeline, which explains the intensity of the plan we're about to get into. But first, let's get inside the machine. To make a superconducting quantum chip work, you need an environment that is just absurdly cold. Hundreds of times colder than outer space.
The cryogenic requirement is the single biggest engineering hurdle. It just is. Rigetti's QPUs sit inside a dilution refrigerator where temperatures drop to 1/100th of a Kelvin.
Which is about negative 273.14 Celsius.
It's an insane technical feat just to create and maintain that. So the physical structure, based on the source material, it's designed with 5 nested casings.
Like a Russian doll.
A very, very specialized Russian doll, yeah.
Right.
They act as enormous vacuum flasks, shielding the interior from heat and radiation layer by layer.
And inside that structure, how do they get signals down to the QPU? That seems like the really tricky part.
It is the real complexity. You start near the top, you have these gold-plated copper plates. Those are the temperature stages separating the cooling zones.
Okay.
Then you go all the way down, you reach the mixing chamber, the MXC. It's the lowest, coldest plate, and that's where the critical hardware sits. amplifiers, and the mounts that physically hold the QPU.
But what about the signals themselves?
That's the signal chain. It's hundreds of coaxial cables that have to run through this whole thing, delivering these precise microwave pulses that drive the qubits, and then pulling the data back out.
So you're threading thousands of fragile data cables through the coldest place on Earth without them conducting heat or interference.
It's a nightmare of an engineering problem, yeah.
Which makes the product they're actually selling, the Novera QPU, even more impressive. It's a 9-qubit system.
The Novera is their first commercially available QPU. It's based on their 4th-gen Anka-class architecture. And you might hear 9 qubits and think, is that even useful?
That's the critical question. A $900,000 unit with only 9 qubits. That sounds like a massive price tag for a small machine. Who is buying this?
So the reason it's relevant is its function and its accessibility. The Novera is sold as an on-premises unit. It's designed to plug directly into a customer's existing cryo and control systems.
So you're not buying the whole fridge, just the core.
Exactly. It makes it perfect for advanced R&D groups. They can prototype hybrid algorithms, and really importantly, they can run experiments in quantum error correction, QEC.
And for anyone listening who doesn't follow this day to day, QEC is basically the holy grail. It's the complex process needed to make these noisy quantum machines actually reliable.
It's everything. Having a dedicated machine to test those methods is a huge deal. Plus, the architecture of the Novera itself matters. It has tunable couplers for faster, more precise 2-qubit operations.
Which boosts the fidelity.
Directly boosts it. And it uses a square lattice for denser connectivity. So it's this focus on fidelity and control, not just the raw qubit count, that makes industrial groups willing to pay nearly $1 million for it.
It's a real physical product being shipped. It's not vaporware.
And that commercial availability is the launching pad for their really aggressive scaling roadmap.
It has to be aggressive. They've got that SPOC valuation to justify and competitors breathing down their neck.
Right.
Here's where it gets really interesting, the roadmap. But before we get to the numbers, why is scaling so hard for these systems in the first place?
This is where physics crashes into logistics. To get to fault-tolerant quantum computing, you probably need, 10,000 to 1 million physical qubits, somewhere in that range.
A huge number.
A huge number. And the moment you try to build that with a traditional setup, it just fails spectacularly. The amount of wiring you need, the amplifiers, the heat load from all of that, it just overwhelms the dilution fridge. It's a hard physical limit.
So if wiring and heat are the bottlenecks, how does Rigetti plan to get from their current systems to over 1,000 qubits in just a few years?
They're betting big on a modular multi-chip architecture. They call it the industry's first multi-chip quantum processor.
So instead of one giant chip.
Right. Instead of trying to make one massive monolithic chip that's impossible to cool evenly and too complex to wire, they connect multiple smaller functional chiplets together inside the fridge.
That sounds smart. You distribute the thermal load, and it must simplify the wiring for each individual piece.
Precisely. It turns a fabrication problem into a modular integration problem. And if we look at the numbers, you can see how this strategy is supposed to play out. Their current system, the 82-qubit Anka-3, already has a really high single qubit fidelity, 99.91%.
And the roadmap just goes vertical from there, with fidelity being just as important as the qubit count?
It's more important, really. By the end of 2025, they're targeting a chiplet-based system with over 100 qubits. But the real goal is a jump to 99.5% median 2-qubit gate fidelity.
And that fidelity jump is what allows for more complex algorithms, better error correction.
It's the whole ballgame. Then, for 2026, the target is a 150-plus qubit system with a projected fidelity of 99.7%.
And the big one,
Yeah.
the 2027 target.
That's the moonshot. Deployment of a full 1,000-plus qubit system, pushing fidelity to 99.8%. If they hit that combination of scale and fidelity, that will define who the leaders in this sector are.
To make that kind of roadmap a reality, you need serious cash and serious partners.
Which brings us to their recent momentum. It was spearheaded by a major financial injection, the finalized $35 million equity investment from Quanta Computer.
Quanta is a giant in high-tech manufacturing. This can't just be about the money.
Not even close. This deal is a strategic collaboration. The two companies are jointly investing over $100 million over 5 years. It pairs Rigetti's quantum R&D with Quanta's world-class manufacturing expertise.
They know how to build things at scale.
Exactly, and that's what Rigetti needs, and we're already seeing it pay off. They recently secured purchase orders for about $5.7 million for 2 Novera systems.
And who bought them?
This is the most important part. It wasn't just an academic lab or a government grant. One order was from an Asian tech manufacturing company, the other from a California-based applied physics and AI startup.
So this is the start of real industrial application. Material science, quantum AI modeling.
A $5.7 million purchase order for physical quantum hardware. I mean, 5 years ago, that would have sounded like pure science fiction. Now it's a line item on a P&L.
The market noticed too.
Oh, it did. The stock jumped over 15% on the news. It shifted investor sentiment from very cautious to moderately optimistic, though we have to add the nuance here, right?
Of course.
It's still firmly in the category of a speculative quantum investment with extreme risk. The potential returns are massive, but so are the risks.
That nuance is always critical. And beyond the sales, they're strategically attacking those scaling bottlenecks we talked about.
Yes. They have a major $5.8 million contract with the Air Force Research Lab, working with a company called QPOP-X.
And what's the goal there?
It's radical. They're trying to achieve stable entanglement between their superconducting qubits and optical photons.
Which is aimed squarely at replacing that huge tangle of cryogenic cables with light.
Exactly. Optical fibers have a tiny footprint and basically zero thermal conductivity compared to copper. If they can translate quantum information from the electrical domain to the optical domain, they solve the heat and wiring problem at the same time. It's a potential game changer for getting to 1,000+ qubits.
They're also broadening their ecosystem with other collaborations.
Right, with CDAC in India on hybrid systems, and they're supporting standards like NVIDIA's NVQ-Link to integrate AI supercomputing with their quantum machines. And their work with Montana State University is also important.
How so?
MSU is the first university to install a Rigetti QPU on premises. That's building the academic pipeline, the testing environment you need to push this tech into the field.
So what does this